Recording in progress. Recording stopped.
Hi, can people on Zoom hear me? Please say hello.
Hello. Yeah, it's audible.
Okay, thank you.
So maybe we need a couple of minutes just to make sure the screens are here. Good. You can now start. Okay. So I'm just with a specific number, and I think in Zoom also.
Yeah, there's people. There's quite a lot of people on Zoom.
Okay, good. All right. So welcome to the second lecture, and today.
Recording in progress.
Today, Guy will speak about miniature triangle metrology and CPU variation measurement. So,
Okay, well, I thank you for coming along today. Yesterday was so I remind you, this is the format of these lectures. I was asked to give 4. So yesterday we had an introductory lecture covering what is the importance of flavor physics and now experimentally how we do this, particularly which environments are good, whether you go to an E+D- machine or a hadron machine. And I spoke quite a lot about the LHC and the LHCb experiment, tried to explain the essential features. And I will come back and give examples, particularly from LHCb in today's lectures. So we finished with a rather hurried digression on hadron spectroscopy, which is not flavor physics per se, but something that one can do well at these experiments. But today I will focus on what is a key task of flavor physics, which is to study the unitarity triangle and make measurements of CP violation. Okay, so This is the roadmap for today's lecture. I will introduce the unitarity triangle and we will look at its key parameters and how we can measure those with a focus on the CP violating ones. When it comes to the CP violation, I picked out certain key channels, key modes, but I should emphasize that there are many, many more CP violating measurements of interest. But these are somehow the benchmark channels. Okay, so let us start with a little bit of formalism. Let me remind you of the well-known CKM matrix and one of its properties, which will be exploited in a couple of slides' time. That this matrix has to be unitary, and the matrix can be parameterized in terms of 3 angles and 1 imaginary phase. And that phase is the origin of CP violation in the standard model. So this is a very tight system of 4 parameters. So it means that CKM physics is highly predictive. So there's a whole host of measurements you can make, and the results of those measurements should be in accord with the standard model. If they're not, then it's telling you that this matrix is larger than you expect, or that superimposed on top of this, there's new physics which is coupling in a different manner. So this matrix can be parameterized in various ways. You find this in the particle data group, but that's not used very often. What is used very often, more often, exploits this very striking feature of the matrix, that it is has this very clear hierarchy with the diagonal elements essentially 1 and the off-diagonal elements dropping away very rapidly. This hierarchy is presumably telling us something. It's very different to the one you get in the neutrino sector, but what it's telling us we don't yet know. But anyway, that hierarchy actually motivates an alternative representation where we can expand it in terms of what we call lambda, which is the sine of the Cupido angle. And this is the well-known Wolfenstein parameterization shown here to order lambda to the 3. So you see now, so I remind you, lambda is like 0.22. So you can see this hierarchy very, very clearly. And you can see that we're dealing here with 4 parameters, not just lambda, but also with A, rho, and eta. And I want to draw your attention to, not that, but to this, that at this order, we have these 2 off-diagonal elements, which are VUB and VTD, which are imaginary, okay? So, so a sort of simple rule of thumb is that if you see any process, any decay which involves VUB or VTD, you can expect that decay to manifest a CP violation, because these are imaginary. Of course, it's actually simplistic and not strictly true to say that the phases of the matrix are carried in these elements here. What actually matters are phase differences, but it's just convenient for me to say that VUB and VTD are imaginary. I should emphasize that this is only the case to lambda to the power of 3 if we and that's very convenient for B physics, but if you're dealing with kaon physics, you are not actually accessing these angles, these elements, you're accessing other elements, and you have to go to higher orders of the matrix to actually see the CP violating imaginary phases come out. Right, so this matrix is unitary, and this imposes various constraints. So in the general form, I write it here. This means you can write down various relations. There are actually 6 independent relations in total, and they can be written out like that. And if you think and ponder for a moment, you realize that these relations are actually can be represented geometrically as triangles in the complex plane. And these relations are known as the unitarity triangle. And there's 6 of them, but the one I picked out here is that. And that's experimentally the most interesting because it turns out that all the sides are of similar length. And the parameters of that triangle can be studied in B decays, particularly B0 and B plus decays. And I will show that triangle on the next slide. But I just want to flag up that there's another relation, another triangle, which is relevant for BS physics, which is this relation here. So maybe I just an interesting aside is that actually all of these triangles will have the same area. And this is known as the Yarlskog invariant. Cecilia Yarlskog actually, for this insight and her contributions to CP violation, she actually won a prize which was presented to her at the EPS conference a couple of weeks ago. All right, so I was hyping this particular triangle, this relation here, and here it is. As I said, all the sides are of a similar length, so this is sort of sketched out here. So you can take this relation, you can then normalize it by dividing through by here VCB star, and you get then a triangle where the bottom of that triangle is of unit length. Okay, so this is a triangle in the Argand plane. You see what the sides are, and you also see these angles. And these angles are phases, things that we can access in CP violating measurements. So if there was no CP violation, this triangle would collapse, and these angles would be just 0, or one of them has to be 180 degrees in that case. But here are the angles, and what I want to point out, I made clear that what's important are these elements VTB and VUB, because naively these are elements which are complex, and you see that indeed. So this angle beta, you see VTD there. This angle gamma has VUB star, and alpha has both of them.
So the reason we normalize by VCB star, that is because they order, they don't have the complex part, right? I mean,
right.
Why, right?
That's right. Yes. So just for that reason, that these are at the order we are interested in for the triangle. These are not complex. So these angles alpha, beta, and gamma, you should be aware that there's an alternative notation which is popular in Japan, which is phi 1, phi 2, phi 3. Rather annoyingly, the phi 1 starts with beta, so phi 1 is not alpha, phi 1 is beta, and phi 2 is alpha. That's something I often forget, but I will be using alpha, beta, and gamma because that's the notation which is used both at CERN and also in the US. Okay, so what's experimentally then, what should we do? Experimentally, what we should do is trying to over-constrain this triangle. We should make measurements of all parameters and see if everything adds up, that we do indeed have a triangle. If we had if the matrix was more than 3 by 3, then we would find that we have some inconsistencies. And we can do more subtle things than this. So we can actually make measurements of parameters, some which are sensitive to tree-level processes. So those are processes where there are no virtual loops. And such processes we know should be completely dominated by the standard model, because these processes are not suppressed. But we should then also make measurements sensitive to these parameters which have loops in them. And those loops, those are entry points for new physics particles. If we can then compare measurements of parameters made in these two manners, then we would, this is a way to probe for inconsistencies, which would signify that, perhaps something very interesting is happening in those loops. There are new particles which have their own flavor structure, not described by the CKM matrix. Okay, so I'll carry on. And I should have said at the start, as as yesterday, you're very welcome to interrupt at any moment. And if you're in Zoom, please just shout up, because I won't be able to see your hand raised very conveniently. So that is the what we call the unitarity triangle, which I'll be discussing for most of today. But let me just preview that there is another unitarity triangle. I said that there's other relations you can write down, and these other triangles are generally much more squashed. And here is one, and this is known as the BS unitarity triangle. It has an angle here, beta S, which is actually very, very small. We'll be coming back to this later. And this triangle is squashed into just a line if you consider the CKM matrix just expanded to lambda3. The fact that the triangle here actually is a triangle only manifests itself if you go to higher orders in lambda. But this will be something we return to right at the end of the lecture, so let's park that for now. Okay, so let's ask, how can we make measurements and probe the parameters of this triangle? So you get these colourful plots. There's two groups, CKM fitter. They take all the data and they analyse it in a very frequentist manner. There's a rival group called UT fitter. These are Bayesians. In the early years of flavour physics this century, they would some of these parameters were not measured very well, so you've got rather different results depending on whether you did a Bayesian or frequentist analysis. And you'd go along to meetings and these people would argue with each other for hours, but that's not physics, that's statistics. Now the quality of the measurements are such that the difference between the two treatments is becoming less and less significant. But you see these coloured parameters coming from constraints like this is a measurement of the angle beta. This comes from a measurement of the length of this side. This comes from a measurement of gamma, etc. And I'm going to walk through some of these and dwell on some of these measurements longer than others. Okay. So the first one I want to measure, to focus on, is the length of this side here, which is it's this ring, this annulus here, right? So this is in terms of the CKM elements, what that length of that side is, and with some very modest assumptions and manipulations, that combination is the same as 1 over lambda, lambda being the sine of the Cabeba angle, multiplied by the magnitude of VTD over VTS. So how can we access that? We're going to access that through measurements of mixing. So now I must step back and remind you, or try and explain to you the actual essentials of neutral meson mixing. This is critical for much of the following discussion, so it warrants a recap. So this is a phenomenon which occurs for neutral meson systems. We first found it in the K0 system, then in the B0 system. It was also now being seen in the D0 system, that's charm, and also the BS system. So physically, what causes it? What causes it is the fact that one meson can turn into another meson. You can do this by virtual short range effects. So this is for BS mixing. This is the famous box diagram. So this is involving these two W's. But it can also do it through on-shell long range effects. So here is a K0 turning into a K0 bar. Just going through this intermediate two-pion system. So both of these processes allow one meson to turn into its anti-meson. So let's look at this more mathematically. So if we approach it in that manner, we note that the actual physical states, the solutions of the Hamiltonian, these actually are superpositions of the Flavour eigenstates. If you solve Schrodinger's equation, this is what you get. So here are the Flavour eigenstates, and here are the physical states, often labelled S and L, and that is because these states, this comes from the kaon system. One of those in the kaon system, you have a very short-lived state and a very long-lived state. And so that location has persisted. So you have these coefficients in front, P and Q. These in general are complex, and sum in quadrature must be 1. Now, if you have CP violation, if you have CP conservation, then the physical states turn out to be just the same as the CP eigenstates. And if you perform a CP operation on this, you'll find that this is a CP eigenstate. For that to be so, that requires that this Q over P, the magnitude of that should be 1. No, in general, in nature, it turns out for all these systems, it's very, very close to 1. But in the kaon system, it was found not to be 1. So this was how CP violation was first manifested in the kaon system. And that would be a very interesting discussion to have in its own right, but this lecture won't permit it. But what we find here is the magnitude of P and Q are not identical in the kaon system. There's this parameter epsilon, but the difference is very, very small, 2 10 to the minus 3.
In the definition of the epsilon, the denominator is okay? P minus Q?
It doesn't allow that looks like it should be a plus. Thank you for that. I'm sorry, I'll try and correct that. Any errors you spot, please tell me. Okay. So that's one way CP violation can manifest itself. It turns out for the other systems, like the B systems, the B physics, which we'll be discussing, that that way of CP violation happening turns out to be, no, it's allowed, it should be there, but it's very, very small. This is not how CP violation dominates in the B system. Also in mixing, so this slide is trying to tell you everything you need to know about mixing, because you have this these two physical states that they have in general slightly different masses. So we talk about a delta M, and this is driven by a short range effects. And you have this a width splitting as well, delta gamma, and this is generally set by these long range effects. Okay. So this mixing happens for kaons, for charm, and for the B systems. And interestingly, if we focus on this mass splitting and this width splitting, here normalized by the actual lifetime, or here twice times the lifetime, we see that these parameters take on very different values depending on which system you are in. And this has very interesting phenomenological consequences. But we're going to be focusing on the B system, and one of the things you might note, for example, is that the width splitting is much smaller in the B0 system than in the BS system. And when we talk about oscillations, which I will in a moment, this means that the oscillations are much more rapid here than here.
Just a very right question, right? So for the delta gamma, when you normalize in the sense to the average gamma, let's say.
Yes.
But for the delta M, like you want to think delta M upon 2M or something like that, right? But
why do you normalize by gamma rather than M? Ask a theory. Okay, that's obviously just a convenient choice. Okay.
Right.
Yeah, that's
maybe common, if they want common normalizing.
One thing I should say is that because particularly here, these are, this is driven by these short range virtual diagrams.
Right.
It turns out these mixing effects are highly sensitive to standard model parameters, and they could be easily perturbed by new physics. So actually the size of this mixing and the comparison to what is measured, it's a very finely balanced system. The so-called Jim mechanism is also very, very important. And you are just looking at these, we are actually very sensitive to bounds on new physics, the possibility of if there is new physics and heavy particles contributing in these loops, unless things are finely tuned, they would have really significant consequences, and you would see the effects. So the effect that the fact that we don't see massive effects here, and that the measured values of these are roughly in accordance with expectations. This sets actually very severe bounds on the possible size of these new physics contributions, with certain assumptions about what their flavor structure is and how they couple. So one can set bounds of the order of 10 to the 3 TeV. So in making precise measurements in flavor physics, we are, here we are much more sensitive to very, very heavy particles, and even if we try and produce them directly in collisions at colliders. So that was a digression, but I encourage you to click on this link and learn about the bounds that these mixing parameters set. They are very, very impressive.
So on this slide, delta m by m will be extremely small because delta m as such is so small, and m is of the order of 4-5 GeV. So it will be very tiny in number. So that's a keep it sensible.
Thank you, thank you. That's good to have some. Right, and now I want to move back to the experimentally what we see and how these things manifest themselves. So this mixing manifests itself as actual oscillations. So what it means is if we have if we start with a B0 meson, for example, that as this propagates through space, it oscillates into a B0 bar meson and then back into a B0 meson. It continues to do that. So one sees this oscillation here, and you see that this mass splitting, this delta M, is functioning as the frequency of the oscillation. And of course, this is all within the envelope of the decay. So there's an exponential decay, but within that you have this oscillation term. So what it means physically is if you produce something as a B0 meson, thank you, but that's if I use the board for longer, I'll ask you to turn the light on. So if we see something is produced as a B0 meson, then when it decays, there's a possibility that we will detect it as a B0 bar meson. Okay, so this is a very, very acute feature of nature. In terms of the B system, these oscillations were first observed way back by Carlo Rubi's experiment in 1987. This was observed in a time integrated manner, which means that you started with a collection of B0 mesons, and then you detected them decaying, and some of them are B0 bar mesons, but you've not measured. You don't know how long they've lived. You just know that some of them have oscillated. That's a time integrated measurement. But what you can then do is make a time dependent measurement, where you actually you say I'm starting with a B0, but then you look every fraction of a lifetime. So you look at the decays and you bin them in bins of lifetime, and then see whether they look like B0s or B0 bars. And then you see the oscillation. So this is how they work, how the time-dependent oscillations were seen first by Aleph at LEP, and now very beautifully by LHCb. So this is B0. So this is actually forming an asymmetry. I've not written the expression here, but it comes from this, that you take a B0 minus B0 bar divided by B0 plus B0 bar, you plot that in bins of proper time, and you see this wonderful oscillation. And you see this oscillation, this is over 10 picoseconds. This oscillation is quite slow, and I remind you that for B0, that this delta M here normalized by gamma is it's less than 1. Contrast that with BS, where this delta M is big. So what you expect for BS is that the oscillations are much more rapid. Therefore, they took longer to be seen and to be resolved. They were eventually resolved by the CDF experiment, Let me actually just take this plot and show it to you in more detail because it's clearer. So this is a beautiful recent plot of BS oscillations as made by LHCb. So what you see here is that something which starts in blue, which starts as a B0 and decays in a manner that a B0S would decay, and in red you have something that starts as a B0 bar, which oscillates into a BS and then decays into the final state of a BS. So, yeah, I think this requires a little more discussion. But the final state, if you draw the Feynman diagram of BS to DS pi, if you forget about the possibility of mixing, you will see that if you have a DS minus pi plus, then that has to have come from a BS decay rather than a BS bar decay. I leave that to you as an exercise. So somehow this final state is saying that this is the final state you expect from a BS decay. So if you see this final state coming from something that was originally a BS bar, then you know that mixing must have taken place. Okay, and you see here this very beautiful pattern, which is the mixing pattern.
So the final state is ds minus pi plus for both, right? So the final state is ds minus pi plus for both. So how do we know the initial particle?
Excellent, excellent. Yeah. So the question is, this plot, the final state. I talked about the final state, but to make this plot, you need to know what the initial state was. That's your question, all right? And I'm gonna come to that very shortly. So this is absolutely critical. Yeah, that's experimentally a big challenge, which I'm now going to address. Okay, you cannot make this. You cannot make this measurement. You cannot make this plot unless you know how the meson was born, whether it was a BS or a BS bar. But the final state tells you how it dies. Okay. But before coming to this, let me again emphasize how rapid these oscillations are. Let me also remind you that BS's, these are at the upsilon 4s where Bell 2 is operating, that is below threshold. It cannot produce BS mesons, because BS mesons are heavier. So you can only make these studies at hadron machines. And at these hadron machines, you also need very precise vertexing and good momentum resolution to get a very good time resolution to be sensitive to these wiggles. If your time resolution is poor, then this will all wash out. Okay, right. So again, I will, before coming to this question about the initial state, we come to that, but I can't remember on which slide. So please park that question and allow me to address it when we come to the relevant stage. Anyway, this mixing, I said how wonderful this mixing is. I want to now turn this back and relate to what we are measuring to this unitarity triangle. Okay, so this mixing, this delta M, and I've done it here for the BS case, delta MS. So the key thing is that depends on these, well, you can see what matrix elements it depends on from just this box diagram. It must depend on VTB and VTS. And here you see them, VTS, VTB star all squared. So that mixing frequency is driven by those CKM elements. Now in front of this, there's a bunch of rubbish. Well, there's the Fermi constant, which should be little that, and there's the mass of the meson itself, the mass of the W. But then there's this all this QCD gump here. Okay, so this can actually be calculated not too badly on the lattice, but even better is if you take this and then you divide it by the equivalent expression for delta MV. Actually, delta MD over delta MS, then you get the ratio of VTB over VTS squared, and you get the ratio of the masses of the mesons, and you get some factor. All of this QCD stuff is pretty similar for the BF and BD systems, but it's not identical, but it's of order 1. But this factor can actually be calculated really rather well on the lattice, okay? So therefore, if we can measure mixing in both of these systems, and we can get our lattice friends to help us out, then we can access this ratio of CKM elements, which if I go back, I remind you, is this is exactly what we want to know what the size of this side of this triangle is. Okay, so this orange-yellow constraint here is actually coming from these measurements. In fact, the measurements are now very, very precise. What is giving you the error bar, the uncertainty, is actually the uncertainty coming from lattice QCD. So this is actually, at the moment, a theory-limited measurement. But as the lattice improves, it gets better by the day. Okay, so now I come to the second side, the bottom side we don't need to worry about because by normalization this is trivially 1. But the other side is this side here, which with some very sound assumptions is essentially just VUB over VCB, okay? So VUB here you're probing the furthest off-diagonal element of the matrix and normalizing it by one of the nearby off-diagonal elements. This I don't want to talk so much about because it's a real can of worms and it's also a very specialist business. But what you're, to measure this, what you're really sensitive to, you're wanting to look at, if you look at a beam quark decays into an up quark, so that's a suppressed decay. You can look at this rather cleanly by looking at the B decaying semi-electronically, for example. So here's a W emitted, here's an electron and a neutrino. So you can look at this process, and then you can look at the equivalent process involving a B decaying to a charm quark, which is the preferred way a B likes to decay. And the ratio of those amplitudes will give you what you're interested in, VUB over VCB. So that sounds simple. Of course, though, what the problem is we don't see quarks in isolation. We see them bound in mesons, and then we have all these gluons rattling backwards and forwards, and this makes for complications. And experimentally, if you're trying to access this, you can think of various ways to doing it. For example, you can say, well, I can look at such a decay. I can consider this system here inclusively. That means I'm not going to look for a specific decay. I'm just going to look, for example, whether this system looks light. If it's light, it doesn't have a charm quark. Or if it's heavy, then it does have a charm quark. And I can, in that manner, separate out the two classes of decay. This is what we call inclusive measurement. Or you can look at an exclusive measurement where you say, well, I look at this decaying, for instance, here to a pion. A pion is definitely a B to U transition. And you can do that, but then you need more QCD inputs to understand what the form factor is, for example, of producing the pion. So there's these different approaches. Rather irritatingly, and throughout the whole history of modern physics, more or less, these approaches have never given exactly the same result. So the precision on these two ways of measuring VUB has improved significantly with time, but there always seems to be a 2 or 2.5 sigma discrepancy between the two approaches. So the measurements get more precise, they get closer together, but they always remain about 2 sigma apart. And the same is, yeah, please.
Which of those two values will agree better with the unitarity?
Right, yeah, it depends which parts of the unitarity triangle, yeah, depends which other measurements of the unitarity triangle you compare it against. But that's a good question.
Do the other measurements of the unitarity triangle also have a lot of theory going into it?
No, this is what I want to make very clear. So this does, and you're very right that you can then, decide which of these you prefer by comparing with the other measurements. But it depends which sets of measurements you compare with. That then determines the conclusion you reach. Okay, but these are now getting rather precise. So even if you assign a generous uncertainty to allow for this discrepancy, you're in good shape. But okay, so I don't want to dwell more on this because, as I say, this is a can of worms, but it's a very interesting can of worms. What I want to do is now to focus on the actual CP violating these angles, which are measured in CP violating manner. And so these are maybe before doing that, and now if we step back, if you look at the width of this green annulus, this is somehow telling you the precision of this VUB over VCB measurement. So you see, it's not bad. But if we want to, the idea is always to shrink these down, and to shrink this down to make this really thin, we really need to get a grip on top of this problem. But let's talk about these two angles. I'm not going to talk about the angle alpha at all, and that's, you can make measurements which are sensitive to alpha, but in fact, alpha is actually, those measurements are actually, if you look at the diagram, you're actually just probing the same quark transitions you are here and here, but you're probing combinations of them. So the alpha measurement is not something distinct. It's nice to have these measurements, but in some sense, it's just a bad way of making a beta and a gamma measurement. So what we should focus on are these measurements. So let's now focus on the beta measurement, and we approach this by discussing decays of B's into CP eigenstates. So a CP eigenstate, if you, for instance, and this is the golden mode J psi K short. K short actually is not a CP eigenstate. A CP violation was actually discovered in the K-on system, and K long and K short are not CP eigenstates, but they are very, very, very close to CP eigenstates. So from the point of view of B physics, this approximates to a CP eigenstate, and we can make very precise measurements without worrying about that distinction. Okay, but you can see if you J psi K short, if you perform a CP operation on that, you get what you start with. And now the potential for making clean measurements of CP violation in the B system, and because of the size of that triangle, it was appreciated right at the start that there you'd see substantial CP violation as compared to the K-on system when it's very small. There are a couple of papers which appeared in the 1980s. So there's two eminent theorists still with us, Icarus Biggie and Japanese gentleman Sander. Interesting digression that the co-author of the Sander paper is this gentleman here who's actually passed away. But this is Ashton Carter, and he actually had a change of career, and he actually served as the defense secretary in the Obama regime. So I think it's always in the UK. All our politicians they studied law or PPE at Oxford, but here you have an example of someone who was actually a professional scientist for quite some time. So he co-wrote one of the sort of key papers which we are going to draw on here. Okay, so this is the formalism. So this is again coming back to the mixing. So this sort of CP violation we're going to be talking about only manifests itself through this mixing. So we start with a meson that is B0 at time equals 0 or B0 bar at time equals 0. And I apologize, I've still not explained how we know that, but I will. And then we see it decay into this CP eigenstate at some time t. So here are the expressions, no time to derive them when you have the decay, but then inside you have this structure. So delta M is again this mass splitting, so it's the frequency of the oscillation. But you have in front these coefficients which are written here, and I will discuss these coefficients. So what we have is that, again, so the B0 can decay directly into the CP eigenstate, or the B0 bar can decay directly into the CP eigenstate. That's why CP eigenstate is of interest. Or you can have a mixing between them and then the decay into the CP eigenstate. So you have these variety of paths, and the interference between the variety of paths which gives this structure here. Okay. Now, it's the CP violation, and why do we need a variety of paths? Well, we're looking for CP violation, that's manifesting itself as a complex phase. If we just had a single amplitude with a single phase, then when you square that, you lose any sensitivity to the phase. So that's why you need two paths. That's why the mixing is needed, okay? So that allows for interference as here. So these are just written, these are a bunch of parameters. So how can CP violation happen? It can happen in a variety of ways. It can happen actually in the decay, and this is called direct CP violation. This is when the magnitude of these two amplitudes would be different, okay? Now, I can already give you a spoiler alert for this case. That turns out not to be the case, or it turns out to be the case at a negligible level. Now, if we look forward to my later discussion, we'll be talking about CP violation in charged meson decays. There you cannot have mixing, and so this is the only way you can get a CP violation in such decays. Another way you can get this is when there's you have CP violation in the mixing, and this is where I already mentioned this, where the magnitude of Q over P is not equal to 1. This is called indirect CP violation. So this is telling you that, well, it's telling you just this and not repeat it. Again, this turns out to be important in the kaon system. In the B system, this actually is at a very, very low level. What is key here, and what turns out to be significant, is when you have this parameter lambda CP here. If the phase of that is non-zero, then what this means in practice is you're getting interference between the decay and the mixing. There's a phase between this, and that phase, and this gives you CP violation. And this also is sometimes called indirect CP violation. And this is the most relevant for the cases we are discussing. So, so we're considering the classic case J side K short, and actually this parameter here, you can express it as CKM elements, and we're interested in the phase of these elements. And what's key is you have VTD in it, and I told you VTD is imaginary. The phase of VTD is beta. You have a VTD on top and then a VTD star on the bottom, so you have a phase which is 2 times beta. Okay, so the imaginary part of this is sine 2 beta. Okay, so what you can do is how does next slide look? Yeah, what we do is rather than just measure the decay rates, we actually form an asymmetry. So we look at things which were B0 bar at birth, and we subtract things that were B0 at birth, normalized by the sum, plotting this as a function of proper time. And what you get is an oscillation, sine delta MT. This is the mixing we saw before, but the coefficient we have is sine 2 beta. Okay, this is theoretically clean. It's known as the golden channel, and it's theoretically clean because the only relevant amplitudes which are contributing are the straight decay and the mixing, and I will sort of emphasize that point in a moment. So measuring this asymmetry allowed you to measure this angle beta. Okay, so to actually remake this point in terms of the Feynman diagrams, so here maybe I should have shown that earlier, but here you see the tree level decay where the B0 is giving you J sine of K short, so you just have this B bar to C bar decay here, a C and an S bar. Simple, right? This diagram has no, if you look at the CKM elements, none of them are imaginary. This though is the mixing diagram, the box diagram, and you have this imaginary part here is dominated by the top quark, so you have BTD and you have BTD here. So the interference between these two diagrams, the imaginary phase you pick out is twice that of the phase of BTD. So this gives you the sine 2 beta. And you so there's no, as we said, there's no direct CP violation. What that means is that there's no interference between this tree-level decay and another decay which does not involve mixing. You can draw other diagrams. This is another such diagram, which is a penguin decay, which in principle gives you the same final state. Well, it does. And this decay also has phases involved, but this decay is very, very suppressed compared to this decay. In fact, the phase structure is very similar. So that is why we say that there's no penguin contribution here. There's no direct CP violation, and the relation I showed you is very, very clean. Now, if this diagram were to contribute, then as well as this sine term, you actually also get a contribution from a cosine term with its own coefficient. And if you see a cosine term, that tells you that this diagram is maybe not as insignificant as you expect. And this means that what you're seeing is not quite as clean as you imagine. So bear that in mind. Okay, so have these things been seen? Well, this has been seen. So this was a great achievement of the B factories. So if you go back to the start of the millennium, in 2001, there were measurements made of this very key CP violation. So this was seen by both Barbar and Bell. So here you see this asymmetry, which I've discussed. Just focus on J side K short. You can actually do the same thing for J side K long, and you just expect the sign of the asymmetry to be different. So you see a wiggle coming from the oscillation, and this wiggle has, this wiggle has a finite size to it. Here, this isn't very impressive because this was the very first measurement. Bell's looks better, I think, but if you added this together, it was significant. And with time, the quality of these measurements improved dramatically. So CP violation was seen. With that, it was possible to get some handle on what the value of beta was, and you could then look at the CKM triangle, the unitarity triangle, and say, is this what I expect beta to be if I compare it with the other parameters of the triangle? And the answer was yes. So this was a very satisfying confirmation of the CKM paradigm. So this enables that the 2008 Nobel Prize was then awarded to Kobayashi and Mascara, having this was experimental demonstration of their principle, their paradigm was correct, at least the first order. So should we not stop there? Well, no, we want to measure this CPA symmetry better. Why should we do that when it remains a golden observable in phase physics? The interpretation is pretty much free of hadronic uncertainties. It's involving this box diagram, and that's of great interest because in that box diagram there can be new physics particles lurking. So we want to measure this as precisely as we can and then compare it with predictions from other measurements of the triangle. And so that's what we're doing. So my experiment LHCb has now made a very precise measurement of sine 2 beta. So you see, if you compare this with the Barbar and Bell plots, you mean, again, the fact that you see a sine curve with an amplitude here, this is telling you see CP violation, and the size of that amplitude tells you what sine 2 beta is. You also see that this curve is very much a sine curve. You can actually look to see if there's any cosine there. within the uncertainties there is not. So this is telling you that indeed your interpretation remains very, very clean. What you're seeing is just indirect CP violation. The direct CP violation is at a very low level. Okay. So this is the world's best measurement. What maybe is of interest, though, is that you compare it with where the B factories left off. The measurement is better, but not infinitely better. And this is perhaps puzzling because the statistics are very different. So at Bar they had something like 10,000 of these decays, whereas at LHCb we have almost 500,000. So I say this measurement is better than they have, but it's not that much better compared to the statistic. So you may ask, why is that so? Yes.
And you are talking about the statistics, maybe you can point this out that over time, since you are plotting the horizontal axis T, the number of particles are reducing. So that's why the statistical
Thank you.
uncertainty.
Yeah. So the fact that this is tiny and here it's very large, that's because you are at 12 peak seconds. And the B has a lifetime of just over a picosecond. So,
I hope you don't mind because there are students.
No, please. That is very, very welcome. Please make any such observation.
Look at a plot and look at all aspects.
Yes, thank you.
In the same queue, maybe if you go back 2 slides back.
2 slides back.
No, there may be more. This one. So again, you can point out that if there is a initial state going to a final state via 2 possible different paths, there will be interference. 2 or 3, whatever.
Yes.
So they should remember always that from a given final initial state going to a final state, if there is a possibility of multiple paths, then there will be interference, and which is evident here.
Yep.
In the left hand middle.
Yes.
So I would like the students to also appreciate the same thing.
Thank you.
The third one also is the third path, but as you mentioned.
Yes, yeah. The whole name of this game is you need the same final state to be accessed by
because of that.
by more than one path, and this will be a common refrain. So thank you.
And the interference terms gives you that dependence where you can utilize.
Okay. Right. So now I'm just. I want to just emphasise why, despite LHCb has hugely more statistics, why it doesn't do quite as well as you might expect compared to Bar. And this, I finally come to this issue of knowing what the initial state is. So this I'm going to explain as concisely as I can. But in all these measurements, you need to know, as my friend there pointed out, you need to know whether you start with a B0 or a B0 bar. So how do you know that? Well, you cannot know that for certain because this is not observable, but you can infer it statistically. What you benefit from is the fact that you have 2 Bs produced in the event. So maybe this one here would eventually turn into a B0. Remember, a B0 has a B bar in it. This rather confusing notation. So a B0 has a B bar quark in it. And this decays to a J psi K short. So, and it may mix, but this is how it was born, right? Because it had the B bar in it. So how do we know that? The way we can access that information is the fact that there's the other B in the event. Okay, so that other B will turn into a meson. Let me just consider the simplest case. If it turns into a B minus meson, and then I think the easiest case to imagine is if this decays semi-leptonically, so a B minus meson, how does this go? So we have a B U bar here. If this decays semi-leptonically, then you're going to get, say, a mu minus there. And you're going to get some hadronic system. You don't really care about that, but the key thing is you have a lepton. You have this gives you a mu minus lepton, okay? So what you can do is you can detect that lepton, and the fact is you detect the charge, and it's mu minus, and that charge tells you what B was when it was produced. And from this, we infer that the other B was a B bar. Okay, you got it? And this is known as, in B physics, this is known as flavor tagging. Right? Now, this should be contrasted with, if people of you who work on high PT physics on CMS, flavor tagging, you use that word just to tell you whether the jet has a B in it or a C in it or an S in it. In B physics, flavor tagging refers very specifically to this procedure, a way of inferring how the B was when it was produced. Okay, so this is the simplest method, that you look at the other B in the event and you see if it decays to a lepton, and the charge of that lepton will tell you something about what this B was when it was also produced. Now, you will not always be right, because firstly, this lepton, you can get a lepton coming from a B to C decay, and that lepton would have a different sign. Also, I've conveniently drawn the B here as hadronizing into a B minus. This B could hadronize into a B0 bar, and then that B0 bar could itself mix and oscillate. And therefore, when that decayed, the lepton which comes off would depend on how often it had oscillated. So this is not always right, but it's statistically, it's going to give you a very good indication. The lepton is just one way to do it, and we don't need to dwell through all of these. You can also look for kaons coming from the other B, for example. And the charge of the kaons will also have a correlation through a similar process. There's also, you can look at for things, for instance, when the B of interest is produced in the fragmentation process. If you're producing a B0, then there will be the fragmentation which produces that hadron will preferentially produce a pion with a correlated charge close to it in phase space. So none of these are absolutely golden signatures, but if you just look at them, or you look at as many of these signatures as possible carefully, you will get a good idea of what the flavor of the B you are interested in was when it was born. Okay, this is flavor tagging. Now this is how we do it at LHCb. We can't always manage it for every event, and sometimes we get it wrong. And we can then parameterize this combination of how often we get it wrong, how often we actually manage to do it. You can turn this into what is called an effective tagging efficiency. And here you see for LHCb, you see it's of the order of 5%. And this is telling you essentially of all the decays you've reconstructed, how many of these are useful. It's essentially saying that for 5% of these decays, they are golden and you've got everything right. It's like the 95% of the decays you could throw away, but the remaining 5%, you know what's happening there perfectly. Okay.
So, which aspect of detector design goes into the kind of determining something like how do you improve?
Well, one thing is you need to detect muons very well, but also I say you can detect kaons, which are very strong in doing this, and so you need good particle identification. But you're essentially, but in the end, you're limited by the environment, because the LHC, the collision, there are so many tracks produced. There's things you cannot fight, for example, the mixing, the oscillation of the other B. There's a finite upper limit to how well you can do. So you can probably also, you cannot get this number above 10%.
Okay, so I guess that is the question what Robin was saying. Like, let's say even if experimentally you do as great 100% of thing, still that the other aspect that you explained. So that's about 10%.
Yes, that's right. Now, this is at the epsilon 4s. I'm not going to I want to leave this as a sort of exercise for the student, but I'll be happy to discuss this. What I'm saying is at the epsilon 4s, so this is the E plus E minus machine where there's no extra tracks, you just have the B and the B bar, and they're produced in the B and the B bar are produced from a decay of the epsilon 4s, so they're quantum entangled. Here, this mixing, how I actually have it? No, I thought it was in the dial. But this mixing is this tagging. It works much better. It works about you do at least rather than getting a an effective tagging efficiency of 3%, you can get it up to 30%. And that's why the events you get at the epsilon 4s are much more valuable than ones you get at the LHCb. So there's two basic reasons for this. The first reason is there are many fewer tracks. So for this to work, you need to be sure you are getting tracks from a B decay. But if you imagine the LHC, because there's hundreds of tracks, you could easily pick a track which is not from a B decay. Okay. The other reason is more subtle, and I want you to think about that. The reason is at the epsilon 4s, you get a B and a B bar produced together in a quantum entangled state. I've told you that these B and the B bars, as they go through space, they oscillate. So at the LHC, when they are both produced, if you have a B0 and a B0 bar, they immediately start oscillating. And that causes problems because that dilutes your tagging efficiency. At the epsilon 4s, this oscillation does not start immediately. The oscillation only begins when one of the B's has decayed. Okay, so you can have a B and a B bar that they could fly millimeters apart, but no oscillations begin until one of those B's decays. Right, so that is I want you to think about that. I'm not going to take 5 minutes explaining it now in the lecture, but that's a specific consequence of quantum entanglement and the quantum numbers of how these B's are produced, right? So it's a very beautiful feature of doing B physics at the epsilon 4s. It's a sort of very practical manifestation of the EPR paradox. Yes.
Sorry to bother you again. Since we are talking about production, maybe you can also mention that when they are produced, they are mass eigenstates, but all these decays, etc., they are related to the weak eigenstates.
Yes, yes, yeah. I mean, by decaying,
these are all weak processes.
Yeah, indeed they propagate through space as a physical eigenstate, but they are detected as a weak eigenstate. Okay. I should, I don't want to outstay my welcome as I did yesterday. Let me, so that question I posed to you, please think about that and we can discuss it. But this is how well we know beta now. So we know this parameter very, very well. The way it's being led by LHCb. Bill 2 is now taking data again. It's going to strike back. I emphasize that this sometimes is forgotten because it was measured in the early days of the B factories. And people think this parameter is measured, we don't need to measure it anymore. We need to measure this as well as we can. This is really a fundamental parameter of nature. This measurement, in this box diagram, there could be all sorts of weird, new, funky things lurking. We've got to do a good job here. Atlas and CMS, those of you working on CMS, there's no reason at all CMS cannot make this measurement. It does, it's J side K short. J side decays into 2 muons. This is ideally suited to CMS. Why CMS and Atlas have not tried to make this measurement, I don't know. It's just a complete waste of their data. They should do it. Okay. Right. I'm going to now just talk more briefly. I think I'll just talk about one other parameter, and then I will conclude today's lecture. So we've talked about beta. Now I want to talk about gamma. So this is another category of CP violation measurement, but the methods here are somewhat different, and that's of interest, I think. But again, this really exposes the beauty and how we can exploit quantum interference. So at the LHC kernel, this gamma uncertainty was like bigger than 20 degrees. You see this enormous range here. This is from 2009. So this is from making direct measurements of this angle, and I will explain how we do that in the following slides. But what we want to do is not, we want to see how the triangle as a whole looks, but from what we know about the rest of the triangle, we can get an indirect prediction of what gamma is, right? So if we know what beta is, if we know this length, we know this length, we know we can get an indirect prediction of gamma. And the indirect prediction of gamma, it says the gamma should be 66 degrees with an uncertainty of about 2 degrees. So what we want to do is to make a measurement which is of the precision of about 2 degrees. And we compare our measurement with this prediction, and any discontinuity, any mismatch would show that something interesting was happening. So how do we do this? So gamma, this angle, we can measure this best in actually charged B decay. So in some sense, it's much easier to think about. No need to worry about these oscillations. And here it's very, very simple. We can just use tree-level processes. If you look at B minus going to D0 K minus, here is a tree-level process, and this has the element BCB. Here you can draw another way of getting this decay, but here we're not getting a D0, we're getting a D0 bar, but this involves a B to U transition, and so you have VUB. VUB is where this imaginary phase is carried. Yeah, this phase is actually gamma. So if we can get these two diagrams to interfere, then we are going to be sensitive to the phase of VUB, which is gamma. How do we get these to interfere? We need the final state to be identical. So we must reconstruct these where the D0 and the D0 bar has decayed to the same final state. And there's many ways in which this can happen. For example, if you ask the D0 to decay into K plus K minus, D0 bar can also decay into K plus K minus. This gives you the interference. So you want to reconstruct such a final state and then compare the rates from when you have B minus decaying to B plus decaying. And that gives you the CP violation. Because under CP violation, the sign of the CP violating phase, here gamma, will actually flip. So here you see this in action. So what we're seeing here are these two diagrams interfering. This is a mass peak here where the D has decayed into K pi with a specific charge configuration. But the thing is that this final state of the D can be accessed by both of those two tree-level diagrams I've shown you. What you see is the mass peak coming from the B. Everything to the left of this mass peak, this is background. But this is from LHCb. You see the background is very nicely isolated from the signal. And what you see is that the size of this peak, the B plus case, is hugely different from the size of this peak, B minus. People tell you that CP violation in the standard model is small, but that's not the case at all. The phases of order 1, you just need the right measurement to pick it out. I mean, the right measurement in B physics, you can pick out these enormous order 1 effects. This is CP violation in action. And the actual, without needing to go through the formulas, one can actually compare from the relative rates of these two things, you can actually very, very cleanly extract gamma. There's actually no hadronic uncertainty. There are hadronic factors which are involved in these decays, but they can be fitted and extracted in the measurement with no theoretical input. This is a beautifully clean measurement. Okay. Here we see another such B decay, also very, very clean. Again, this is telling you about gamma. I'm not going to, okay. Finally, so it depends on the final state you're looking at. In all cases, we're looking at B to DK, but the D we're insisting is going to decay in a manner which both D and D bar can go to. What I've just shown you there were just two-body decays, beta, where the D went to K pi. You can do more complicated things. You can look at a three-body decay, for instance, K short pi pi. And there, rather than look at the absolute rate, you make one of these things called Daleks plots. I showed you this yesterday. So this is the final state for K short pi pi, and you calculate the invariant mass of two of the final state particles, K short pi minus. You square that and you plot it against the invariant mass squared of the other two particles in the decay. And you get these beautiful pictures which are showing you, all these bands are showing you the intermediate particles which are existing between the D and the final state K short pi pi, such as K stars, rhos, etc. So that's what's driving the density you see here. But what is of interest is, again, you compare between B plus and B minus. Superficially, these look similar, but if you look more carefully, you see that there are differences. Here, there's more the differences here to here and here to here. And you can actually quantitatively analyze those differences. I think time does not allow us to dwell on that. And this also gives us very clean information on gamma. We now know gamma. We've measured it to like a precision of 4 degrees. So this is 4 to 5 times better than when the LHC turned on. But I remind you that the other constraints in the triangle say that we know that what this should be to something like 1 to 2 degrees. So at the moment, gamma is where we expect it to be, but we're not measuring it, though we're measuring it very well, we're not measuring it quite as well as we need to. So we need to really kick on here and get these uncertainties down. So qualitatively, so where have we come with our studies of the unitarity triangle? So this is this triangle. This is way back in 1995. So this was before the B factories turned on. There were no direct measurements of CP violation in the B system there, so we knew nothing about beta and gamma. What we did know, this band here comes from kaon physics, and we knew a little bit about the mixing. So we had a very rough idea where the apex of this triangle was. And the fact that it's displaced up here is telling us that, we had some idea that indeed it was a triangle, but really this level of knowledge was very, very poor.
Any input in these from the lab experiment?
LEP may gave information on the, and on VUB to some degree. You get to the B factor in 2001, the first measurement of sine 2 beta. So you see this in blue here. Those early wiggle plots I showed you from Barbar and Bell, that was already telling us that, that was lining up with pretty much where you expected the apex of this triangle to be. So that was already very exciting, but still rather crude. In 2009, by 2009, the precision on sine 2 beta is now really rather good. This triangle is really clicking into shape. And what the key point is that all of these garish coloured bands are lining up with a common vertex. So this is telling you that Kobayashi and Mascara's description of flavour structure in nature and CP violation is correct, at least it's correct within the precision of this measurement. So that's impressive, very impressive. And this is essentially now, there's not a more up, this is the most recent such plot that's been made. Now this gamma measurement I told you about is now really rather precise, but not as precise as we want it to be. Here is the mixing, so this is limited by lattice QCD. This annulus here comes from these measurements of VUB over VCB, and sine 2 beta, remains impressive. So things are lining up, but what you can do, this was when you alluded, you can zoom in here and you see how tightly things actually are lining up, and you can analyze each contribution very critically. So we've certainly come a long way, but we need to do further. Though it's consistent, there are certainly new physics could still be lurking there at the 10% level. So new measurements are vital. One other interesting manner of looking at this is that you can look at this triangle using measurements which are sensitive just to tree decay. So this gamma measurement I've just shown you, that involves no box diagram. So that's interesting because tree level processes should be driven almost entirely by the standard model. Also, measurements of this annulus, though experimentally they're difficult to make, that's a tree level process. So this is somehow, the way these overlap, though not very precise at the moment on its own, is telling you, this is really in the standard model how the triangle looks. And then you can compare that with the other measurements, and all of these other measurements involve loops. So an interesting way to look at the unitarity triangle is not just to look at it as a whole, but to differentiate between those measurements and these measurements. If you do that, I mean, it depends which measurements you use, but many eminent commentators, they say, well, I can see tensions here at the 2 sigma level, the 2.5 sigma level. I think the broad message is that things are looking overall things looking very consistent, but there are some intriguing signs of tension, which that just encourages us to make better measurements. I will finish there, but my slides, which I encourage you to look at, I said that there was this other triangle of interest, which was much more squashed with an angle beta S in it, and that is accessing. So this is somehow like the sine 2 beta measurement, but it's a measurement you can make in the BS system where the oscillations are much more rapid. And here you access the phase associated with BTS, which is imaginary, but it's only imaginary if you look at the CKM matrix, the higher order. So here it's not imaginary, here it is. So this is a very, very small CP violating effect. The measurements are very interesting. You make it with BS to J psi phi. It has a long history, but this is where we are at the moment. So this is the value of phi s here plotted against the width splitting in the BS system, which is finite. In standard model, you expect this phase to be very, very close to zero, but not exactly zero. And this green shows you the latest measurement from LHCb, and this is about 2 sigma from zero. So we have a situation where what we see here is again looking consistent with the standard model, but we need to improve the quality of the measurement significantly. And this is also a place where CMS and Atlas can contribute because the final state is J psi phi. We can use dimuons. Okay, so thank you for your attention. So I hope to convince you that study of CP violation is important. The CKM matrix holds lots of mysteries, and there's lots of measurements we should continue to make. So thank you for your attention.
Yeah, sorry. So, if this unitarity breaks down at some future level of precision, what is the kind of new physics you would, like a new generation of parts? So,
yeah, there's two things that we could do that. So if you had a 4th generation, yes, that would show the thing to break down. But more trivially, that if you had in all of these diagrams, like these box diagrams I showed you, if you have rather than the standard model particles, if you had a new physics particle there, that new physics particle has its own flavor structure, so it would have it would have to couple in a particular manner. So what that manner is, we don't know, but that would certainly mean that what you measure in general would be different from what you predict based on just the CKM picture, right?
So like extra, it could be supersymmetric, I mean, let's say supersymmetric particle or extra gauge boson or things that can come to this group.
Yeah. So in crude terms, well, this is the BS case, but what I showed for the BD case, when you're measuring sine 2 beta, you think you're measuring sine 2 beta, but the presence of new physics particles in the loop would mean that you're not measuring sine 2 beta.
So a new interaction with the new sector to the gauge group?
Yes.
Or a new generation?
Yeah, so in general, that's what, I mean, any new physics should come in with its own flavor structure. And so all the measurements we make at the moment, we interpret them saying that we just have the standard model particles. But that interpretation, if there's new things there, that interpretation would be wrong. That's why it's critical to differentiate between tree-level processes and loop-level processes. Tree-level processes should be unpolluted by this new physics. So there the interpretation should be good. But when we say we're measuring sine 2 beta, if there's a new physics particle in the box, then very likely we're not measuring sine 2 beta.
Okay, so before we take more questions from the room, can we hear any questions from the Zoom, people in the Zoom?
Well, I can see it. I think the Zoom's still there, but I don't see any hand.
Okay. So maybe while people are, so yeah, please go on.
So in continuation to Thomas's answer, whatever he did. Basic point is that we are essentially measuring rates. If rates are different, that means there is something beyond standard model. And the interpretation has to be consistent with the whole set of global measurements. So just from one rate measurement differing, you cannot say there is a problem in the coupling, in the gauge boson, or any particle in the loop that you cannot. So it has to be done in a global.
Yeah.
Every measurement is essentially rate measurement, either of production or of.
Yeah.
Similarly, sorry, another thing I wanted to say is that, as he is saying, let's say Argus measured this oscillation in B system. That was very important, and that also matched with standard model rate, which confirmed the existence of clockwork. That was very important. That Argus measurement of the observation of the oscillation. That clockwork does exist, because nobody was getting it, and it was not very clear whether the third generation has the same thing, whether B is a singlet or a mixed up, etc.
Yeah, we can maybe, if I go back to my mixing, maybe we can, did it was in this, you don't see it here, but buried away in the expression is actually the top mass. So this.
No, earlier you showed the BV oscillation, you mentioned about Argus result.
Yeah, but this one you can take as the delta MD.
Yeah. But I very much agree with your first point. So yeah, a single measurement on its own is not of use. But as I emphasised, this CKM paradigm is extremely predictive. So you have a huge range of measurements you can make, and they should all hold together. This is rather different to neutrino physics, which is now trying to explore a similar sector, but it's sort of at the moment very difficult to make redundant measurements in neutrino physics. Here in B physics, there's masses of things you can do to test self-consistencies, particularly probing processes which should be more sensitive to new physics, those which are less sensitive.
So one comment regarding your comment about why CMS is not able to do so as much of the
Sine to beta.
Yeah. So one possible problem is the acceptance. So J side triggering is not an issue, but within the CMS acceptance of beta equal to 2.4 or 2.5, you can say the kinematically you don't get too many events.
Yeah, unlike LSCB, because the B's are produced in the forward direction.
Okay.
The main problem of CMS.
Effective number of.
It's basically the event acceptance is the problem.
Okay, well.
But the tagging, do you know? I mean, maybe I should. The flavor tagging, like for the LSCB.
You look at the left-hand side of the left-hand side.
Yeah, but
because KM tagging is not possible, right? So which is.
Yeah, no. So for this measurement here, which I didn't dwell on, but yeah, this is maybe J side pi.
Yes.
Yeah, so seeing that you can see does very well. But yeah, I just wondered why they never bothered to measure J side K short. But you're explaining to me that because the K shorts,
In fact,
they fly and you have few of them. But we don't have many in LHCb. We lose 2/3 of them. So I'm not convinced you're in a worse state than we are.
Meant for high PGV physics, and so the sector acceptance is really used.
I'm not.
I'm not.
Okay.
One simple question is that you mentioned that production rate at 14 TeV is 600 microbarn. What should be the better value for 13 at 13 TeV? Which is equal to 13 TeV, 550.
Sorry, I did.
At the beginning of your lecture,
yes,
you were talking about the rates.
And
you quoted the number 600 microbarn.
Yes.
At 14 TeV.
Yes.
You have some idea that what should be the ballpark number at 13 TeV? 13
TeV. Oh, well, that was very approximate. Well, it's only very slightly smaller than that. I mean, it varies very slowly. It sort of doubled between 7 TeV and 14 TeV. Yeah.
Okay. Yeah, please. Yes. So you mentioned about this. Can you speak little louder than that? You mentioned about inequality triangle. So there are other issues like the first row inequality. For example, this Cabiba anomaly.
Yes.
So do you have any comment about that? Like about all the triangles, not the triangle, the diagonal.
No, these unitarity triangle, the unitarity relations. There are whatever 6 of them. And indeed, so there's some which don't involve CP violation measurements, but there's one which, if you look at them one by one, there's interesting questions. Some of them are related to things like just like the measurements of the Cabiba angle, and some of these relations, experimentally, some of the numbers don't add up as well as you wish them to. So there are. You're right. There are anomalies there. I'm not a specialist.
Cabiba angle anomaly is called.
But these are very. They're worth close scrutiny. All I would say is I don't think they fit into a global picture yet, and you say, "Aha, we can explain all these anomalies by this new physics." I think in all cases you want to probe more carefully into how the actual measurement is made. There's measurements like the neutron lifetime and things like this, which you should. So I think always you should dig deeper into the experiment.
Is that okay, Siddharth? So is there any more comment? We have some lattice people, like you are talking about that lattice, like how important that the lattice thing. So it's always more the lattice calculation will come.
Right. Okay.
So this just cross. Yeah, just cross.
I don't know. So I just So thank you for your attention. So next week we will talk about flavor changing neutral currents. I mean, essentially very suppressed processes where we are not necessarily interested in the level of CP violation, but we're looking at processes which are proceed at very high order in the standard model. So these are places where new physics really could perturb what we actually expect to find. And here in recent years there have been some very interesting anomalies which I shall discuss. So in closing, let me just remind the students here, please think about this question of why at the epsilon 4s this mixing is different from at LHC, for example. Why, if you have a B and a B bar produced coherently, does the mixing not begin until one of the B's has decayed?
So what I will say that since we have the next lecture after a few days, that will be, and first of all, the next lecture will be in the AG66, the neophyte room. So the audio video is much easier. So we would request, like, particularly for the student, some of you or few of you can tell that, it's a kind of homework, right? So you think about it, that point he said that why, that only when one B measure decays, then only the mixing thing can, it's almost like a stopwatch, starting at that point, not before that.
Right. So that will take it up as the third lecture. The initial part, some of you can just say, right? Volunteer one of you. So with that, let's thank once again. And
Recording stopped.
yes.
Nice.